In the last lesson, we figured out some of the basic rules of calculus. So as you can see, our addition rule, our multiplication rule, and our inverse rule. Now, we could keep cranking along and trying to find more, but let's just take a step back and think, okay, is there a pattern here? I mean, these look fairly simple, but is there some kind of connection underlying all of them? And there is, actually. Here's the first one. This is sort of the high-level insight that I wish someone told me a long time ago. When we have a system with a few different parts, when we take the derivative, what we're saying is, okay, well, how does the whole system change? And the easy way to think about that is just to say, well, let's say you have a company with 4 different departments, and you want to make a policy change. How do you know what the impact is going to be? Well, just go and ask each department, well, how will this change impact you? You take up the results, and that's sort of the combined impact. And with functions, it's similar. We sort of have this function which is made up of a few parts, and we just want to know what's the contribution from each part. When we have a change, how much will each part contribute to the whole amount of change? So for example, if we have f plus g, f times g, f raised to the g exponent, f divided by g, it doesn't really matter. At the end of the day, we just have 2 contributions to take in mind, f and g. And so if you look at these, both of these rules, they actually look very similar. It's just something plus something. And both of these have kind of a contribution from f and a contribution from g. Now, the next rule, 1 over x, this only has a single perspective because there's only really one thing that's changing here. We can consider 1 as sort of a a dumb, unmoving part, right? So x is a moving part. 1 is never going to change, so its contribution will always be 0. So if you like, you can consider this as a combination of x's contribution and 1's contribution, which happens to be nothing, because 1 will not react to any changes. No matter how much you yell, it's never going to change. So there's really only going to be one piece of the puzzle here. But the other parts, f and g, can both change, and so we'll have contributions from both. So that's kind of a key insight where even if you don't know the exact format that a derivative will have, you can at least count up how many additions there should be. And eventually you can simplify things, but just at a high level, how many little bubbles are we going to have that kind of interact, and or are we going to count and to know what the total change would look like? So that's sort of this first intuition. The next is what I call kind of a dimensional intuition. So again, you're not trying to get the details, you're just trying to get the high-level picture of how things change. When we do a differentiation, right, it's basically a fancy division. That's what it is. It's fancy division. It's a division that can have different amounts at each step instead of the same identical amount. So just like addition, if we're going to divide x cubed by something, by x, we know that the result is going to be x squared. And so we can kind of go down this little chart here. If we have something with x cubed and take the derivative, it should result in something with x squared because we just divided by x, in a way. We did a fancy division, but at the same time, it should just drop the exponent because we went from volume, let's say, to area. So the key idea here is to kind of use it as a gut check. So when you're doing derivatives, you should know that, well, we're kind of doing a fancy division and we should be dropping the exponent at some point because we're kind of turning volume into area. And so this is a really useful gut check to know whether you're doing it properly. And integrals are the same thing. You're kind of going up the chain. You're multiplying, so you're kind of going up the chain. Now, 0 is kind of interesting. If we have 0 dimensions, and it's 0-dimensional in the sense that it doesn't react to anything, it's always there. I think of a 1-dimensional line as sort of spanning, but a point or a constant doesn't actually change, so we can call it sort of 0-dimensional. And the thing here is you actually get stuck. If you keep doing the derivative, you're sort of dividing 0 by x and you get 0. Divide 0 by x, you get 0 again. So you can't really go past this. You need to start here and keep going down, and you kind of get stuck in the middle there. Later on, there's sort of some subtleties, and we can talk about it. But at a high level, you sort of get stuck once you get down to 0. You can't really do much with nothing. So you're kind of stuck at nothing once you get there. So again, this is sort of a very high-level way to look at the patterns in derivatives and how it's changing. And actually using these rules, just the kind of the count them up rule, like how many variables are there, and this little pattern of the powers, we can make some pretty good predictions without even knowing the exact formulas. So earlier in the course, in the announcement, we talked about a scenario. So here it is. Let's say we have a quarter, and we have the Earth. Small quarter, big Earth. We take a string and we wrap it around the quarter. We take another string and wrap it all the way around the Earth. And we decide, hey, you know what? That's too tight. So let's loosen up that string around the quarter to make a 1-inch gap all the way around. And for the Earth, the same thing. It's too tight. So we loosen up that string that's going all the way around the entire Earth. We loosen up that string, so now there's a 1-inch gap all the way around the Earth. Here's the question. Which string did we have to loosen more? I'm not talking about percentage terms or anything like that. Absolute inches. Which string took more inches to loosen up? You can consider expanding the string if you like, or if it's like a loop, you can loosen it up. But which string got longer when we had to do that? So we had one string going like that, one string around the Earth going like that. Now, using our dimensional intuition, we should be able to figure this out. And here's how. The circumference is a line, right? So on this table, the circumference is just a line. It's something linear, something x, right? In the case of a circle, it's 2 pi r, but forget about that. You don't even need to know it. It's just something x. When we take the derivative, that means how will it react to change. When we're making the shape change, how will that impact the circumference? Well, we know that we go down the table and it's just a constant. We just reduce the dimension by 1. So no matter how big you were when you started, when you're changing, the derivative is constant, which means that adding a 1-inch gap around the quarter takes the same amount of extra string as adding a 1-inch gap all the way around the Earth. I know you don't believe me. You probably don't believe me, so it might be kind of fun to try out with a quarter and maybe a basketball or something that's more reasonable, or maybe a dinner plate. But adding that one extra little 1-inch gap only takes about 2 pi inches or 6.28 inches, no matter how big you started with. It's really amazing, and it's sort of something you can derive out of this table. You can sort of think about it and say, okay, we're just dropping a dimension here, so therefore we're going to have a constant change, which means that no matter what we started with, it'll be the same amount. So it's kind of a cool little intuition that we can sort of work and practice with. So with that, hope you enjoyed it. Happy math.